Hello everyone. In today's session, let us look into the most requested video about maximum likelihood hypothesis for predicting probabilities. We already know what is the maximum likelihood hypothesis. It is a hypothesis that minimizes the sum of the squared errors over the training examples, right? So now let us see what is the predicting probabilities for this maximum likelihood hypothesis. Let us understand the problem first. It is to learn a non-deterministic function f where x is mapping to the target value 0, 1, or learn a neural network whose output is probability that f of x is equals to 1. Stated in other terms, learn a target function f dash where x is mapping to 0, 1 such that f dash of x is equals to p of f of x. Okay, so the probability of f of x being 1 is taken as f dash of x. Okay, let us understand this more clearly with the help of an example. Let us take x, the instance space, as symptoms of the medical patients, and let's take the target function f of x as 1 if the patient survives, 0 otherwise. So here the case that we are taking is we have a training set or a set of patients who are having all similar sort of symptoms related to a particular disease. Okay, suppose if we take the case of COVID scenario. Okay, so there what are the common symptoms? Everybody having high fevers and then cough. So in some people they have vomit, some people have motions. So like that, some symptoms are there for this particular disease. So like that, we have a set of patients. So now, though some patients have similar symptoms, do everybody survive during the COVID situation? No. So some have survived, luckily, and some have not. So now, let us also imagine that f of x is the probabilistic function, and we are assuming the patients with similar symptoms, out of them, 92% might survive. So then, since they are surviving, our f of x value is equals to 1. So like that, how many are surviving? 92%. So f dash of x is 0.92. And 8% are not surviving. Okay, so they may not. So your f of x value is equals to 0 and f dash of x is equals to 0.08. Okay, so this is our problem. We should make our neural network to learn this representation. Let us see what is the scenario or the target concept where we can help the neural network to learn this. So for this, let us assume certain assumptions that our training data, capital D, is taken as set of instances or training examples in the form of x1, d1, x2, d2, so on up to xm, dm. And we are also assuming that the xi and di are random variables and each training example is drawn independently. So then using Bayes' theorem, we can write the probability as P of D by H is equals to pi of I equals to 1 to M, P of Xi comma Di by H, right? And one more assumption what we are taking is the probability of encountering any particular instance Xi is independent of the hypothesis H. That means we are not looking at the hypothesis and picking a particular instance. Let's understand this with the help of an example. That is, the probability that our training set contains a particular patient Xi, it is independent of the hypothesis about the survival rate. Okay, so we are not taking that into consideration. Randomly, we are picking one Xi. So then we can rewrite our equation 1 using product rule as P of D by H is equals to P of Di by H comma Xi multiplied with P of Xi, right? So now let us apply the case that, so let us take one instance where our target value, so that is the target value bi is equals to 1. So what is the case that it will be 1? So if you take p of di by h comma xi, what I want my di to be 1. So I can rewrite it as 1 by h comma xi. This is equivalent to h of xi. In simple terms, I can rewrite this as h of xi. So I will reformulate my p of di by h comma xi as h of x. So why am I taking 1 by x? Because all events are likely events and they are independent of each other. So each event has an equal probability of getting the value 1 by h. And here h of xi, whenever my di value is equals to 1. Otherwise, it is 1 minus h of xi. Whenever di value is equals to 0. So now from this, and let us also take the probability into account. So let us take the binomial distribution. So as per that, I can rewrite my p of di by h comma xi as h of xi to the power of di 1 minus h of xi to the power of 1 minus di. So let us check whether both are same or not. So first let us take di value as 1 and substitute in this. I'm changing my color just a minute. So let us take the h of xi value as 1 and try to substitute in this. So then I will have only my h of xi to the power of 1 and this term is going to become 0. 1 minus di value is 1, 1 minus 1 is 0. Anything to the power of 0 is 1. So I have h of xi when my di value is equals to 1. Similarly, let us take the di value as 0. So h of xi to the power of 0 we are taking now. So then the first term will become 1 and the next term will be 1 of 1 minus h of xi. Okay, so which is equal to this second case. So I can say that let us take this equation as 3, the first one. Let us take this as 3 and let us take this as 4. So I can say that 3 and 4 are equivalent. So I can re-express this equation like this. So now if we substitute this value in our earlier equation, that is P of d by h is equals to I is ranging from 1 to n. Okay. So in place of P of di by h comma xi, we are taking h of xi to the power of di multiplied with 1 minus h of xi to the power of 1 minus di multiplied with p of xi. And let's apply the maximum likelihood hypothesis on this. So as per maximum likelihood hypothesis, what is HML? It is Argmax. H belongs to capital H. P of d by h. Okay, some people are troubling with the binomial distribution. Okay, so for your convenience, I'll give you the formula of binomial distribution also here. Just a minute. So as per binomial distribution, we can write P of r as n factorial divided by r factorial into n minus r factorial multiplied with P of x to the power of r multiplied with one minus P of x to the power of n minus r. So here we are observing one sample. Okay. So n value we are taking as 1. So here this will become 1 minus r and this term will vanish. So I will only have, in place of r we are taking bi. Here our p of x is h of xi. So it is h of xi to the power of bi multiplied with 1 minus h of x to the power of 1 minus b. Okay. So that is how we got this value, this particular, right? Okay. So let's continue our discussion. So now let us apply this argmax on our formula. So that is HML is equals to argmax, which belongs to capital H. Phi of I is equals to 1 to n h of xi to the power of bi multiplied with 1 minus h of xi to the power of 1 minus bi multiplied with p of xi. Okay. So now from this equation, if you observe this p of xi, the probability of picking xi randomly, okay. So each and every instance has an equal chance of being picked. So moreover, this value will be same and it will be a constant value. So let us ignore this particular term and only take this particular part. So it is argmax, which belongs to capital H. Phi of I is equals to 1 to n h of xi to the power of bi multiplied with 1 minus h of xi to the power of 1 minus bi. So now, what is our aim? I want to minimize the sum of the square error. But here what is happening? Here I am having a product term. So that means I will get a maximum value, but I wanted a minimum value. So I want to convert this product to summation. So if I want to convert this to summation, let us apply a logarithm on this. Okay. And whenever I'm applying a log on this, so log A into this, I'll just give you the formulas also here. Log AB is log A plus log B, and log A to the power of n is n into log A. Okay, so both I'm doing here. So this is our power factor, so that should come into the front. So di multiplied with log h of xi. Okay, since these two are terms are in product, I am applying a plus on this. And the power I am bringing to the front, it is 1 minus di log 1 minus h of xi. So these are maximum. So now if you compare this, if you remember the decision tree concept where we were working with the cross entropy. Okay. So there, what we have, so the formula that we obtained there is minus pi log pi, right? So where we will be working with both positive and negative instances. So now here, if you observe, this is the case of positive instances, and this is the case of negative, that is non-survivor. So I can consider this HML as negative of cross entropy. So now let's see how to train our neural network to learn the weights. So here we will be using the gradient search to maximize the likelihood in a neural network. We are already aware that how gradient descent works, and here we are, the aim of this is to derive a weight training rule for neural network that seeks to maximize the gradient of h comma d using gradient ascent. Here we are not using the gradient descent method, but we are using gradient ascent. We initially start with gradient descent only, later we change it to gradient ascent. Carefully follow, you will understand. We already aware that the gradient of g of h comma d is given by the vector of partial derivatives of g of h comma d. When we work with back propagation, so there we have applied this partial derivative on the g of h comma d with respect to various network weights. And here, let us apply the same concept. Let's apply the partial derivative of g of h comma d with respect to weight wjk. So whenever we write wjk, since we are back propagating, it is from input k to j. Okay. So it can be written like this. Sigma I is equals to 1 to m dou of g of h comma d divided. So one second. I'll take one. So we are performing a partial derivative with respect to wjk. So and let us also apply the chain rule with respect to dou of hxi. So because we are working with respect to the hypothesis only, so we are introducing this h of xi using the chain rule. And we already know the value of this g of h comma d. So just now we have obtained the maximum likelihood hypothesis. So the same thing we are taking here, okay, which is di into log h of xi plus 1 minus di into log 1 minus h of xi. The remaining is as it is. Okay, so now let's apply a partial derivative on this and let's simplify. The partial derivative of log x, that is dou of log x with respect to x is 1 by x. So with the help of this formula, let's try to simplify this part. So it is sigma I is equals to 1 to n pi. So here I have log h of xi. So it will become 1 by x. So di by h of xi plus 1 minus bi. And here, since I have a log term, it is 1 by 1 minus h of xi. And I have to apply partial derivative on this 1 minus h of xi also. So it is minus 1. So here if I apply a partial derivative on h of xi, the value is 1, so I need not consider. But it is minus 1, so we should mention this. So if you simplify this, the remaining term is as it is. That is h of xi. The other part we didn't solve it. So now if you simplify this part by taking LCM, so you will be getting h of xi. Okay, this term will vanish because we applied a partial derivative. I'm sorry. It is h of xi into 1 minus h of xi. So if I simplify this, this is what I'm obtaining. And here, di into h of xi gets cancelled. Positive and negative are getting cancelled. So finally, we are left with the terms di minus h of xi divided by h of xi multiplied with 1 minus h of xi. And we have the other term, that is dou of h of xi divided by rho wj. And now here you should remember the sigmoid activation function. So if you take a derivative on sigmoid activation function, we will be getting rho y into 1 minus rho y, right? 1 minus rho of y. So that is the speciality of the sigmoid function. It is derived. You can perform derivative on. So using this formula of sigmoid, so we can rewrite our dou of h of xi. The second part we are doing h of xi divided by dou of wjk as rho dash of xi multiplied with xi j k. So you should remember the back propagation here. Okay. So I can rewrite this whole part like this. So now in place of this, I can use this formula, and here we are taking h of xi into account. Okay. So it is now, so I can rewrite this as rho of h of xi. Sorry, not none of this row. H of xi multiplied with 1 minus h of xi multiplied with xi j k. So let's keep both together and let's see the gradient. If we put together these two values, so here in the denominator of the first term, you have h of xi multiplied with 1 minus h of xi, and this term will come in the numerator, h of xi multiplied with 1 minus h of xi into x3. So this term will get cancelled. So finally, we are left with di minus h of xi divided by, not divided, multiplied with xij. And here we have a summation for 1 I equals to 1 to n. Okay, so this is what the gradient descent result that we have obtained after performing the partial derivative. So this is what we have obtained. So to update the weights, this is the formula that we will be using gradient descent. Wjk is wjk plus delta wjk. So where delta wjk using gradient descent is minus eta into dou gh comma d divided by dou wjk. So the result of this we have obtained as di minus h of xi multiplied with xijk, right? So as per the back propagation, it should be minus eta if you are taking gradient descent. But our aim is not to minimize, but we want to maximize. So instead of taking gradient descent, we want to take gradient ascent. So we take a positive value here. So delta wjk is plus eta sigma I is equals to 1 to m di minus h of xi multiplied with xijk. So here we are assuming a single layer perceptron only for simplicity. So finally, we can conclude that. So whenever this is the formula that we will be using for weight updation. So finally, what we can conclude is these two weight update rules. Okay, so when they will converge toward maximum likelihood hypothesis is the rule that minimizes the sum of the squared error seeks maximum likelihood hypothesis under the assumption that the training data can be modeled by normally distributed noise. Okay, so what if any noise is added to the network, it should be a normally distributed one. Okay, so when we are taking the cross entropy, so it seeks the maximum likelihood hypothesis under the assumption that the observed Boolean value is a probabilistic function of the input instance. So I have shown you only one weight convergence. Okay, let me show you the other one also. So for that, you should remember, just try to recollect the back propagation, what we have derived. So if you remember the back propagation derivation, so there we have obtained delta Wjk as eta Oj into 1 minus Oj multiplied with the error term what we have obtained. So now here we want to minimize the sum of the squared error, pk minus ok whole square, right? So that thing here we are expressing it as h of xi into 1 minus h of xi. So why are we expressing like this? So the probability of a patient being survived is h of xi, not being survived. So this is what the output we are expecting, right? Whether the person is survived or not survived. So it is h of xi multiplied with 1 minus h of xi. Okay. So this is the formulation of delta Wjk. So in the first case, we have seen this. This you can use when you are applying the cross entropy. And the second formulation you can use when you are working with the sum of the squared errors. So finally, what we can conclude is whatever maximum likelihood hypothesis that we have obtained, so it is going to minimize the sum of the squared error when the training data is modeled by normal distributed noise. And when you are using cross entropy, then the observed Boolean value is a probabilistic function of the input instance. Hope you enjoyed the video. If you have any queries, do post in the comment section.